Let's have a look at this exercise. Here we have that water is being heated from 25 to 100 degrees Celsius. And the question asks, how does the chemical potential change? So, I've written a few things out here that you have seen before. First of all, the chemical potential is symbolized with this character, and for a pure substance, it's also equal to the molar Gibbs free energy. So, there's very little to this question in terms of what's being asked, but there's a whole lot to think about. So, if you really consider what they're asking, they're asking you, how does the chemical potential change with temperature under a condition of constant pressure? And we gather the constant pressure condition because I'm just heating water from just above room to boiling, and there's nothing else being said, so I'm going to assume that that's on the bench. And therefore, if it's just on the bench in the lab, it's under a constant pressure. And so, it's the change in the chemical potential versus temperature at a constant pressure. I know from previous work that this is equal to a minus Sm, and if I have forgotten, that's okay, because I know how to derive that. I would start with G is equal to H minus Ts, and then expand that differential to dG is equal to dH minus TdS minus STD, and then open up the dH and so on. And it would swell and get larger number of terms before it reduces down to just 2 terms on the right-hand side, at which time I divide through both sides by dt at a constant pressure, and the solution to the right-hand side would simply be a minus Sm, or the molar entropy, negative. So this is a plot, the slope of a plot, exactly, of the chemical potential versus temperature for a pure substance. And to sketch this, I like to draw this line first, the steepest slope, and then a neighboring line that intersects, lesser slope, and another one of a lesser slope, but still a negative slope. So where those lines intersect are my phase transition temperatures, where the solid changes to a liquid and the liquid in turn changes to the vapor. So this is my melting and my boiling point. I'm going to open up the brackets and say that dgm is equal to minus Sm dt, or if you like, write it in terms of the chemical potential variable. And then I want to integrate both sides. And so I get the change in the chemical potential, or the change in delta G, or the change in G, is equal to, and the question is, can I bring this outside of the integral sign? Well, the real question is it constant? So you would tend to think that the molar entropy is going to change for the liquid as you're heating it. But if we go back to this graph, hopefully this will become a little more clear for you. Recall what the molar entropy is. It's the slope of the straight line. And so really, I have a constant slope, which means that the molar entropy of the liquid is a constant value over the liquid range, because there's a single value for the slope, and the molar entropy is equal to the negative slope. So that can actually come outside of the integral, and then I'm left with the integral of dt, which is simply delta t. So this I can actually look up in a table. I know it's not given in this question, but it's given at the end of the text in a data table. And negative Sm is negative 69.91 joules per k mole. And the delta T from 25 to 100, whether you leave it in Celsius or convert it to Kelvin, it's still going to be 75 degrees. And so my change in the chemical potential, you see I know it's going to be negative because it'll be the final minus the initial, the final G minus the initial G, so a smaller number minus a larger number, which will be negative. So let's just turn on the calculator. 75 times 69.91. And I get a change in the chemical potential, which is the change in the molar Gibbs. And that is equal to 5243 joules per mole. And I'll just move that up a wee bit. Let's put it in kilojoules. So 5.2, I guess. And it's a negative. 5.2 kilojoules per mole. So that's how much the chemical potential changes per mole of water. So if I had a volume, I would use the density to bring it to a mass, and the molar mass to bring it to a number of moles, and I would get then just the straight value of delta G in energy units for that amount of water. So this is actually a really good question for you to think about. So you'll find that in Chapter 4, and perhaps you can put it away for a little while and come back to Part B, which is quite similar to A, and see how you fare.